everyone, welcome back to online survey video tutorial on applied hydraulics. So today we are discussing about the one more type of reaction turbine, that is the Kaplan turbine and its components. See, based on the direction, we have a different types of turbines like radial flow, axial flow, mixed flow type of turbine. So whatever the previous turbine, that is Francis turbine, we have discussed, that is a radial flow turbine. So this Kaplan turbine is an axial flow turbine. So what is the meaning of axial flow turbine? See, if the water enters, water flows parallel to the axis of rotation of the shaft of the turbine, then that turbine is called axial flow turbine. So, and here in case of axial flow turbine, the shaft will be vertical, and also the lower end of the shaft is made larger, which is called as hub or boss. And also on that particular hub, the vanes are fixed. Hence, that hub will act as a runner. You can see here, this is a shaft which is vertical, and the lower portion of the shaft is made larger, which is called hub. On the hub, you have a vane, so that's why this hub will act as a runner. And coming to the types of axial flow reaction turbine, so we have two types of turbine, that is propeller and Kaplan turbine. So what is propeller and Kaplan turbine? See, if the vanes are adjustable, whatever the vanes which are fixed on the hub are adjustable, then that is called the Kaplan turbine. So if the vanes are non-adjustable, that is called a propeller turbine. Okay, so let us see what is Kaplan turbine, by the way. See, it is named after as an Austrian engineer, which is who is V. Kaplan, and it is a axial flow low head reaction turbine. So this is best suitable for a low head high flow rate condition, and so it is suitable for a head of 2 to 25 meter, so flow rate of 70 to 800 meter cube per second with a specific speed of 255 to 860 rpm. And also, so you can see the figure here how this Kaplan turbine will look like. So you have a shaft, and so the shaft, the lower end of the shaft is made larger, which is called hub. So on the hub you have adjustable vanes. So these are adjustable vanes. And coming to the main parts of Kaplan turbine, so the first part is scroll casing, guide mechanism. You have a hub with a runner, hub with a vanes, which acts as a runner, and draft tube. So these are the components of the Kaplan turbine. You can see here you have a casing, that is a scroll casing. After that you have a guide vane here. So the water enters from casing to guide vane, and guide vane will direct water to the hub with the runner with the vanes which are more adjustable. So those will act as a runner vane, and you can see this is the shaft. And after the water passed on to the runner, it will be get discharged through the tail race through the draft tube. So you can see this is the draft tube, so which is used to discharge the water to the tail race. The purpose of all these components, so you already know. So the same purpose, the purpose remains same for all the parts of the Kaplan turbine. And so here also you can see, and here dB represents the dia of the boss, and D naught represents the outlet diameter. Okay, so this is how the Kaplan turbine will be there. And coming to the flow in turbine, so the first water enters into the casing through the penstock, and you can see after the casing the water is enters into the guide vanes here. So the guide vane will direct water. So from the guide vane, water will turns 90 degree. So you can see here, so it will turn into 90 degree and enter into the runner. So where parallel to the axis of rotation. So that is how the flow will occur in case of Kaplan turbine. And here for a Kaplan turbine, the discharge is calculated using the formula Q is equal to pi by 4 D naught minus dB cube into VF1. So where VF1 is the velocity of flow at inlet. And some of the working proportions which you should know is the peripheral velocity at inlet and outlet, that is U1 and U2 is equal to pi D naught N divided by 60, and here VF1 is equal to VF2, that is velocity of flow at inlet and outlet are same. And also the area of flow remains same both at inlet and outlet, which is given by pi by 4 d naught square minus dv square. So these are some of the working proportions which are necessary to solve the problem. Thank you all. Let us continue in the next class.